What we are seeing in last class? Types of matrices. I think we have seen everything except one. The last one is singular and non-singular matrix. Excuse me. Yes, please. If you are writing these things, you can put one small subheading. Singular and non-singular matrix. If you didn't know anything about matrices, you should listen this. In next chapter, we will learn something called determinant of a matrix. I'm not sure. I think you would have learned in physics, in torque or something, to find determinant of a 3 by 3 matrix. You will write now cross product. You will do A cross B for two vectors. There you are doing determinant, but you are expanding using row 1. You can also expand using different rows here. Determinant, if you learned in school, you would have known, or else we will learn little later in next chapter. So like if you are following this, please put one small subheading. Last type with rows and columns here. Again also we have different types. Those things are not with number of rows and number of columns things, right? Number 11 is what? I think in 11 we are seeing singular and non-singular matrix. Yes, please. Yes, please. Please close the door. A square matrix of order n is said to be singular if determinant of A is equals to 0. Determinant we will also write det of A is equals to 0. We learn about this in detail in next chapter. For a definition, you can write this. A square matrix of order n is said to be non-singular if determinant of A is not equals to 0. Det of A is non-zero, determinant is defined for only square matrix. It is not defined for rectangular or different types of matrix. If you need one example, I'll give you here. If you don't know anything about determinant, I can tell you a small glimpse I'm giving here. A matrix A, you take 2 by 2 matrix, 1, 2, and then S please. 1, 2 I'm taking. This is a 2 by 2 matrix. Like for 2 by 2 matrix, A, B, C, D is the elements of the matrix. Determinant of A is equals AD minus BC. Product of diagonal minus product of non-diagonal. Product of principal diagonal minus product of non-principal diagonal. This is 1 into 2 minus 1 into 2, which will be 0. This implies matrix A is a singular matrix. So you can take B is equals to 1, 2, 2, 2 by 2. Determinant of B, if you are doing this, is 1 minus 4 minus 3 not equals to 0. B is an example of a non-singular matrix. I think he studied in 11th grade, no? AD minus BC is the determinant formula for ABCD matrix. ABCD is 2 by 2. A, B, C, D. Saras and all in 2 by 2 you will do. That is what you want. 3 by 3 only, no, you will do Saras. Okay. So next, we are seeing operations on matrices. Like, first of all, let me tell you what operations and all we are seeing on this matrices. Then we'll write in detail. AC is too cooler. We will see first of all equality of matrices. When we'll say two matrices are equal, you know when we say two real numbers are equal, we know when we say two like functions are equal, right? Two variables are equal. Here also when we'll say two matrices are equal, that will be coming under equality of matrices. After equality of matrices, we'll be seeing addition of matrices. After addition of matrices, yes, please. Scroll down. Why? Which one? This one? From here. Let them copy, please. You guys can proceed. The third one we'll be seeing multiplication of a matrix by a scalar, that is known as scalar multiplication of a matrix. Fourth one, negative of a matrix. Equality of matrices, addition of matrices. Third one is scalar multiplication. Fourth one is negative of a matrix. Fifth one is difference of matrices. Sixth one is trace of a matrix. Seventh one is transpose of a matrix. Important is transpose. One more thing I missed. Important. Multiplication of matrices. That is also important. You can add whatever thing we have, like we will see equality, addition. After addition, we will see scalar multiplication, negative matrix, difference of matrices. After that, we will go multiplication. After multiplication, we will see trace and transpose, right? And their properties. I suggest you to listen when we are going from multiplication of matrices, from where you will see something extra than NCRT. I don't think you have seen those all things in NCRT. Remaining all is basic things. I'll just give what is that, one small example and moving forward, right? So let me write them. Scrolling up. Third one, scalar multiplication. Fourth one is negative of a matrix. Fifth one is difference of matrices. Sixth one is multiplication of matrices. Seventh one, trace of a matrix. Eighth one, transpose of a matrix. In this, few are basic, but important is multiplication, trace, and transpose. Remaining all are basic things we are learning, right? So starting with first one, equality of matrices. And equality of two matrices. Two matrices A and B are said to be equal matrices if 2 points will be there, their order is same, maybe if their order is equal. Second one, their elements are equal. Right? So like if we are taking matrix A and matrix B, we will say matrix A will be equals to matrix B if the order of matrix A is equals to order of matrix B. It is not necessary A and B are square matrices. You can also have rectangular matrix, but they are equal as well. Order is same and each and every element is same. Mathematically, we will say matrix A is equals to Aij order m by n, and matrix B is equals to Bij order m by n, right? We will say that if A is equals to B, then Aij is equals to Bij for all I comma j. Clear? This is mathematically we can write in this way. Maybe if you want small example on order 2 matrix, like square matrix I am taking, it is not necessary to be a square matrices. I am taking for example, A is equals to A1, A2, A3, A4. This is a second order square matrix. B is equals to B1, B2, B3, B4. A is equals to B implies that AI should be equals to BI for all I is equals to 1, 2, 3, 4. A1 should be equals to B1, A2 should be equals to B2, A3 should be equals to B3. Clear? This is what equality of matrices. Now maybe I can have one small problem here. I can connect equality of matrices to relations. Now, let's say R is a relation. Inside R, you have two matrices M1, maybe M comma N are matrices such that M is equals to N. So here M comma N belongs to set of matrices of same order. Can anybody here tell me what kind of relation is this? Matrix M is related to matrix N if M is equals to N. Both M and N are the matrices from the set of matrices of same order. You can take second order matrices. You are defining a relation R on second order matrices on set of all second order matrices. Clear? And then you are taking two matrices M and N when they are equal. I am asking what kind of relation is this? Identity relation. Equivalence sounds correct to me. Right? So we can say here like M is related to M. Replace N with M. You will have M is related to M na, that is reflexive. If M is equals to N, then that is symmetric. If M is equals to N is equals to some other variable, you can take maybe O, right? M is also equals to O. This is transitive. Clear? Therefore, the relation R here is reflexive. In our book, they have given a relation defined on set of matrices of same order is equivalence if they are talking about equality of matrices. Equality on matrices is also equivalence relation. Now, after equality, what is the second one we said? Addition of two matrices. So, how to add two matrices? We cannot add matrices to random matrices. Addition of matrices is defined only if they are of same order. Not necessary to be of squared matrices, but both should be of same order. A and B is of same order, then only A plus B is defined. If A is 1 by 2 and B is 2 by 1, addition is not defined. Right? So we are taking let A and B are two matrices of same order. What do I mean? I mean, let's take A is equals to Aij in compact form. Order is M by N. B is equals to Bij. Order is M by N. Now, A plus B is a matrix that is defined as Aij plus Bij M by N for all I comma j. Clear? Not require the matrix to be a square matrix. It can be of. You can add two row matrices. You can add two column matrices. You can add two rectangular matrices, but you need to make sure they are of same order, or else it is not defined. Maybe if you want a small example, let us take a small example of second order we are considering. Let us take matrix A is equals to A1, A2, A3, A4, and B is equals to B1, B2, B3, and B4. I'm taking here. So now if I'm adding them, A plus B is equals to right? What I can say here, I can add the element of row 1, column 1 element, I should add with row 1, column 1 element. Row 1, column 2 element, I should add with row 1, column 2. Same thing for remaining elements as well. In A plus B, I should write A1 plus B1, A2 plus B2, A3 plus B3, last is A4 plus B4. Subtraction is also same way. Before learning that, you should learn in between things, right? Row 1, column 1 with row 1, column 1, same thing you should add. This is your addition of two matrices. Like again, I can say here addition of two matrices like of same order is a binary operation. I think you would have learned about binary operation in first chapter, right? There you would have learned no addition of two real numbers is a binary operation. Correct? Didn't learn. Say something, no? See, like binary operation, you give two inputs, collect one output. If it is happening for every two inputs, there is an output, then that is binary operation. In another words, technically binary operation, star is said to be a binary operation if it is a function defined from set S cross S to set S. Two inputs you are giving, only one output. Addition, multiplication is a binary operation on set of natural numbers, whole numbers, integers, and then whatever real numbers you have, everything. Clear? Matrix addition is also a binary operation, is what I am saying. Clear? So next, the properties we will see. From childhood you are seeing, no? Addition of two real numbers is commutative. Commutative means you understand what is commutative. A plus B is equals B plus A. Addition is also associative. Correct? So like for addition, you have identity element. You have inverse element. That is what we are seeing now in properties. These are all basic things you should know. So we are learning properties. First one is commutative property. A and B are of same order. I am not mentioning. I can write A plus B is equals to B plus A for all A comma B belongs to matrices of same order set. Maybe we write in this. Second one, matrix addition is associative. What do we mean associative here? If you have three matrices of same order, then only addition is defined. A plus B plus C is equals A plus B plus C. After associative, there is a lag. 1 moment, please. Next, associative. Tell me guys, what do you know about identity element for addition of two real numbers or addition of two numbers? Let's say I'm talking about addition on natural numbers. Do you think identity element is exist in that case? When we are talking on set of natural numbers, there is no identity element for addition. What do I mean identity element? A plus B should be equals to B plus A, that should be equals to A. Clear? So like if you take normally for addition, the identity element is 0. A plus 0 is equals to 0 plus A is equals to A. In set of natural numbers, there is no 0. So identity element does not exist. In matrices, identity element exists. Can you tell me what is identity element in matrices? Or identity matrix for addition, I mean
Null,
normal, not right. Sorry? Null
null
matrix, perfect.
matrix.
Null matrix. A matrix plus null matrix is equals to matrix itself. Null matrix na all zeros. A plus O is equals to O plus A is equals to A. O is a null matrix here. Identity element for matrix addition. So can you guys say something about inverse element? For natural numbers, for whole numbers, for integers, anything you can take. Anybody, inverse element, please. What do you know about inverse element? See, like inverse element na, for addition, if you are talking about inverse element, we should say A plus B is equals B plus A is equals identity element 0. That means B will be equals to minus A. In matrices also you have something like that. We say A plus B is equals to B plus A is equals to null matrix. That means the matrix B is equals to minus 1 into matrix A. This is known as negative of a matrix, right? So here minus A is inverse element for A. Next we can write about scalar multiplication. Multiplying a scalar to a matrix, right? Third one, some doubt is there? No, right? Can I scroll up everybody? Whoever writing, I'm talking with you only. Scalar multiplication. Scalar, I mean some real number. For a matrix, number 3. You have seen, I think vectors you didn't study, right? In vectors you will understand. Scalar and vector, two things will be there, no? In matrices, scalar means some real number, not a matrix. Scalar multiplication for a matrix. So here it is not necessary that the matrix should be a square matrix or something like that. This is exist for any matrix. You can take any matrix of any order. Alpha be a scalar. Scalar means just a real number, not a matrix. In that case, alpha into a, let us take A is equals to Aij m by n. When you are multiplying a scalar to the matrix, that means you are multiplying the scalar to each and every element of the matrix. One example we take, let's say A is equals to A1, A2, A3, B1, B2, B3, C1, C2, C3. It is a third order or like order 3 square matrix. If you are multiplying a scalar to the matrix, you should multiply that scalar to each and every element in the matrix. Here you can learn one thing. You cannot take something common from the matrix unless until it is there for each and every element. Let's say if there is a common element in row 1 or row 2, you cannot take that one out in general. You can take out only if it is there in each and every element, each and every column and row as well. You guys copied this? Can I scroll up? Whoever writing? So like here, basic properties of scalar multiplication we should learn. In properties of scalar multiplication, scalar multiplication is distributive over addition. Alpha into a plus b is equals to alpha a plus alpha b. I can also say k plus L into matrix A is equals to k into A plus L into A. Small alphabets are scalars, capital alphabets are matrices. Scalar multiplication is associative as well. What do I mean? Alpha into beta matrix A is equals alpha into beta matrix A. Let's say if you are multiplying a matrix by 0. 0 into matrix A is equals to scalar into matrix A will be equals to null matrix. If you are multiplying 0 to each and every element, that will be a null matrix. Clear? Anything I missed here? What is next after scalar multiplication? Negative of a matrix. Negative of a matrix, we can say it is a special case of scalar multiplication. We are multiplying with -1 for the matrix. Can I scroll up? Everybody copied this. Number is 3, I guess, in operations of matrices. Anybody who wrote? 4. Okay, 4. Negative of a matrix. A is equals to Aij order m by n. Negative of a matrix is minus A, that is minus Aij order m by n. This is any matrix. This is negative of matrix here. You need any example? Let us take one small example, second order. A is equals to A11, A12, A21, A22. negative of matrix A, that is minus A, multiply minus 1 to each and every element. Minus A11, minus A12, minus A21, minus A22. This is called negative of a matrix. Using negative of a matrix only, we will find the difference of two matrices. If you want to find difference between two matrices, let us take differences is also defined if A and B are of same order. Order same, we cannot neglect. If you are neglecting, you don't have difference or sum in that case. So if you studied multiplication of matrices, guys, can we have product between two matrices if they are of same order? A minus B we write as A plus minus B. Aij plus minus Bij. That is your Aij minus Bij. This is difference of matrices. Next we are going multiplication only. Properties won't be there this much. When you are subtracting two matrices, what you did in addition, same thing. Add row 1 column 1 element to row 1 column 1 here. Instead of add, we should subtract, right? Maybe if you want, I write one example, row 1 column 1 minus row 1 column 1, right? So let us take one small example here. A and B of two odd matrices of second order I am taking A1, A2, A3, A4. This is matrix A. This is matrix B. B1, B2, B3 and B4. Subtraction of matrices A minus B will be equals to A1 minus B1, A2 minus B2, A3 minus B3, A4 minus B4. First row, first column element with first row, first column. First row, second column with first row, second column, and so on. Addition and subtraction is same. Next, I am talking to you guys. If you studied matrices in schools, tell me, can I say product of two matrices is defined if they are of same order? Huh? Yes. Okay. Can you multiply and tell me the result of two column matrices? You take like column matrix 2 1 and 2 1. Hmm? Cannot. Multiplication is not defined is a proper answer. What is the rule? This multiplication of matrices, we can connect to composition of functions. In functions, you would have learned that G composition F, that means G circle F is defined only if the range of function F is a subset or equals to domain of function G. The range of input function is a subset or equals to domain of output function. Clear? Now in case of matrices multiplication, let A and B are two matrices. The product between A and B is defined only if the number of columns in matrix A should be equals to number of rows in matrix 2. Did I said correctly, guys? Did I said correctly? I didn't interchange, right? Okay. Then we will write that. Next is matrix multiplication. This is important. Product between A and B is defined only if the number of columns in matrix A is equals to number of columns in matrix B. You would have seen in schools. Can we say matrix multiplication is commutative? Matrix multiplication satisfy commutative property? No, in general it is not, right? So when it will commutate? If you know anything, just tell me. Huh? All square matrices, huh? You take like any two square matrices, 1, 2, 3, 4, and then like you take like something else other than identity matrix and check whether you are getting commutative or not. You won't. Hmm? No, no. You take two matrices. Some matrices you take from book. That many I cannot remember. No. Two square matrix you are telling. Take order two square matrix, two different one. Find AB and find BA. Check whether you are getting correct or not. You won't get equal. See, like matrix multiplication will be commutative if one of them is null matrix. Zero null matrix. And then one of them is identity matrix. Anything else you have? One is null matrix, commutative. One is identity matrix, again commutative. Do you have anything like this other than null and identity? You learn diagonal matrices in school. Take two diagonal matrices of same order, multiply and check whether you are getting commutative or not. Huh? Don't take identity matrix. If you want, pick your rough notes. Order 3 matrix you take, maybe. Order 3 matrix. 1, 2, 3 is the diagonal for first one. 4, 5, 6 is the diagonal for second one. Try to find the product. Order 3, 1, 2, 3 principal diagonal I have mentioned, remaining all are zeros. Check whether you are getting AB and BA equal or not. See, again listen. For first matrix, it is a 3 by 3 matrix, order 3 square matrix. Principal diagonal elements are 1, 2, 3. Second matrix is again order 3 square matrix. Principal diagonal elements are 4, 5, 6. Check, you will get commutative. We are getting commutative. No response. Calculating. We are getting commutative, my dear students, or not? Don't know. Should be coming. So now listen. If you don't know matrix multiplication, I suggest everybody to listen. Like after matrix multiplication basics, we go properties. There we learn something out of NCERT. Let us take two matrices. Any two matrices I take, multiplication is not defined. So let us define matrix A is Aij, order is M by P. Matrix B is equals to Bij, order is P by N. I can see that the number of columns in matrix A is equals to the number of rows in matrix B. Then AB is a matrix. You can call maybe product as C. In this way we write Cij. Order is M by N. So like maybe in composition of functions you would have learned in this way. Function f is from A to B. Function g is from B to C. When you are doing composition, directly you connect A and C. Now it is MP, Pn. Directly you will take M to N. Clear? So like this is what the matrix multiplication is. Now the matrix multiplication is trickier one. If you are learning first time, I suggest you to listen, right? Maybe we write this note. matrix multiplication between A and B is defined only if the number of columns of matrix A are equal to the number of rows of matrix B. In the same example, if I am trying to find BA, product between B and A is not defined. Clear? Because like I can see one is N, another is M. In general, it is not defined only if M is equals to N. Clear? Understood? So like one example for the one who is learning first time. Let us take second order square matrices. I'll prove here itself matrix multiplication is not commutative using this. AB will be equals to 1, 2, 3, 4, 5, 6, 7, 8. Multiplying row 1 with column 1. If I multiply row 1 with column 1, I'll get first row, first column element. It is like 1 into 5 plus 2 into 7. Row wise, column wise is what I'm multiplying. Again, row 1 with column 1, if I multiply 1 into 6 plus 2 into 8. Row 1 and column 2. Row 2 and column 1, this is 3 into 5 plus 4 into 7. Now this is 3 into 6 plus 4 into 8. This will be equals to 5 plus 14, 19. 6 plus 14, 20, 6 plus 16, 22. 15 plus 28, 43. 18 plus 32, 50. Now if we are finding BA simultaneously product between B and A, 5, 6, 7, 8, 1, 2, 3, 4. Multiply row 1 with column 1. We will get A11 here. 5 into 1 plus 6 into 3. Multiply row 1 with column 2. 5 into 2 plus 6 into 4. Multiply row 2 with column 1. 7 into 1 plus 8 into 3. 7 into 2 plus 8 into 4. We are multiplying row 1 with column 1, we got A11. Row 1 with column 2, we got A12. Row 2 with column 1, we got A21. Row 2 with column 2, that is A22. So I can see here this will be equals to 5 plus 18, which is 23. 10 plus 24, which is 34. 7 plus 24, that will be equals to 31. 14 plus 32, which will be equals to 46. Now clearly I can observe the order might be same for AB and BA, but AB is not equals to BA. Matrix multiplication is not commutative. Anybody writing this part? Can I scroll up? Writing finished? Till here done? So like I have a problem to you guys. In real numbers, if I have x into y is equals to x into z, I can cancel x on both sides. So I'm asking you, does the cancellation loss holds for matrices? If I have A into B is equals to A into C, can I write B is equals to C? Why not no? In what situation it is no, in what situation it is yes? AB is equals to AC. When we will write that will be equals to BC, B equals C. When we write it is not equals to BC. Right, what I am talking is cancellation loss. AB is equals to AC is given. Right, can I cancel A on both sides? If I can, in what situation? Null matrix. One moment please, he's saying something. Null matrix. A and B are two non-null. A, B, C are no null matrix is there, no identity matrix is there. Now tell. A is non-singular. A is non-singular, in that case it is true, correct. Cancellation loss holds if A is non-singular. A is a non-singular means inverse exists. We are multiplying with inverse on both sides. In functions, F composition F inverse is identity. In matrices, matrix into matrix inverse is equals identity matrix. Right? Cancellation loss holds if it is a singular matrix, non-singular matrix, or else it won't. Now properties we will write one by one. Property number one. First one. In general, matrix multiplication is non-commutative. Let under this we are seeing different situation. Why this won't true? Situation one. Let A is equals to Aij M by P and B is equals to Bij P by N. It is clearly mentioned in the problem M is not equals to N. In this case, AB is equals to Cij, order is M by N, but BA is not defined. If BA is not defined, I will say AB matrix cannot be equals to something which is not defined. Even though you say, sir, let us take a situation A is equals to Aij N by P and B is equals to 1. Bij P by N, it is given that N is not is equals to P. In this case, AB we have Cij. Can you guys tell me the order of AB, anybody? N by N. What about the order of BA? BA is not N by N, that is P by P. So like here, matrix AB is not equals to matrix BA because orders are different. Matrix A and matrix B can be equal if their orders are same. Even though you have square matrices, A is equals to Aij N by N, two square matrices you consider. B is equals to Bij, again N by N. In this case, even though AB is equals to Cij N by N and BA is equals to some Dij N by N. Even though orders are equal, the elements may or may not be equal. Here also AB is not is equals to BA for every A and B. There might be some A and B will satisfy this, right? Not for all A and B, it is true. Clear? It fails for majority of things, only some exceptions are there in this case. Clear? Now we will see what are those exceptions. Second one, this is about, maybe at the end we write as a note point. First we finish these all things. The properties for matrix multiplication. After commutative, what we guys see? Associative, right? Second one, see if you want any example, refer above example I am writing. In above example only, no, I have taken two square matrices of order 2. I multiplied AB is not equals to B I got. Next is associative. For associative, A is equals to Aij M by P. B is equals to Bij P by K. C is equals to Cij K by N. So now here I can write AB into C is equals A into BC. You can check that matrix multiplication is defined and matrix multiplication is associative for all ABC of this type. If the product is defined between AB and between BC, in that case, it is true. In this way, if you have. Clear? After associative, we will see distributive. Matrix multiplication is distributive as well. It will follow right and left distributive both. I made sure B plus C is defined, A into B is defined, A into C is defined. So this is left distributive property. This is right distributive. So for matrix multiplication, what is identity element? Identity matrix, right? Then inverse of all matrices does not exist. Inverse exists only if it is a non-singular. About inverse we will see later. I think in next chapter only. Identity element for every matrix is not defined. Identity element is defined for a square matrix. The reason is identity matrix. Right. AI is equals IA is equals. Now I suggest who are sitting in this class to please listen these all things. I am writing these all things as note points. One by one we will see. First one in general. Cancellation loss does not hold for matrices. That means it won't work for matrices. Under one condition it will work. AB is equals BC does not implies that B is equals to C. Right? So when it will be equal? Yes, please. If A is a non-singular matrix, then we can say AB is equals AC implies that B is equals to C. Under the condition the matrix is non-singular, we are multiplying with inverse on both sides and we are making identity matrix in left hand side. In the same way, what we have seen is this is left hand cancellation law. Right hand cancellation law will also hold only if the common matrix is a non-singular matrix. Am I clear? This is first thing. Second thing, guys, in real numbers, we learned in lower grades, if product between two real numbers A into B equals 0, directly we write either A be 0 or B 0. Both can be 0 as well. What do you think for matrix multiplication? If A into B equals null matrix. What I can say about it? O stands for null matrix. Sorry? I give you an example where A and B are non-zeros. If AB is equals to null matrix, then what I can say? A and B can be two non-null matrix. We have one example in our book. Everybody open this. Page number 6, fourth point. They have given two matrices. You take like matrix A is equals to 1, 1, 1 and then 1. Matrix B is equals to 1, 0, minus 1 and 0. So can you guys check whether product is 0 or not? Multiply row 1 with column 1. 1 into 1 plus 1 into minus 1. Row 1 with column 2, 1 into 0 plus 1 into 0. Row 2 with column 1, 1 into 1 plus 1 into minus 1. What we are getting? We are getting 0, 0, 0, 0. AB equals null matrix implies that one can be null, that is also true. Both are null, that is also true. We have a situation, both are non-null as well. In general, it won't imply at least one of them is null. We can say that at least one of them is singular. Clear? But we cannot say at least one of them null. Understood? This is second one. Third one. Matrix multiplication is commutative if one of them is matrix multiplication is commutative. Write this. If one of them is identity or null. So you consider this one as a homework. Take as many examples as you want and check what happens if one of them is diagonal. One diagonal and one normal matrix, square matrix, 3 by 3 you take. Try and check and tell me the result tomorrow. If it is working, we'll write here. One diagonal you take, both diagonal is working. One diagonal and one non-diagonal you take. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9 you take. And this side, you take any diagonal matrix, maybe 10, 11, 12 as principal diagonal elements, multiply A into D and D into A. Are we getting same? If we are getting same, we'll add our diagonal matrix tomorrow. Am I clear, everybody? What I am speaking? If A and B are two diagonal matrices of same order, then AB is equals BA. Normally, this is like we have seen in algebra, no? That kind of things. We can write A into A is equals to A square. We can write A into A, n times you multiply, that will be A power n. We take A power 0 as identity matrix. Normally in algebra, you write A plus B whole square as A square, B square plus 2AB. In matrices, we cannot write that. A plus B whole square is A square plus AB plus BA plus B square. In general, it is not 2AB. If we have I plus A whole power n, binomial theorem we can apply here. This is NC naught into I plus NC1 into A plus NC2 into A square and so on, NCn into A power n. Binomial theorem can be applied on matrices. Clear? I power n minus 1 is I only into A. How many times you multiply identity matrix with identity matrix, you will get identity matrix. Want you add this? I square is equals I cube is equals I power 4 is equals I power 0 is also equals I. After finishing this, we have types of matrices on this A square thing. There is a matrix called idempotent matrix if A square is equals to A. There is a matrix called invalidatory matrix if A square is equals to identity matrix. There is a matrix called nilpotent if A power n is equals to 0. There is a matrix called periodic matrix if A power k plus 1 is equals to A. Clear? These types are there. Next is like we need to see about trace and the properties, transpose and the properties. After that, we should see about symmetric, skew symmetric, Hamilton and skew Hamilton. Am I clear? We don't have that much time to start next concept. So one more thing you can add. We have seen different types of matrices, no? What do you think if I multiply one lower triangular matrix with a lower triangular matrix? What I am getting? You write all these things at the end. At the end, last page or somewhere you go in your notebook. One by one you write. I asked you to try, you try. Come on Thursday and tell me your results. First one, you take A as, let A be a square matrix of order 3. First one, let A be a square matrix of order 3 and D be a diagonal matrix of order 3. D be a diagonal matrix of order 3. Check whether AD is equals to DA or not. Check whether AD is equals to DA or not. Clear? Second one, AD equals DA or not equals DA. Second one, in second, you take if A and B are two lower triangular matrices, then what is AB? If A and B are two lower triangular matrices, Then what is AB? What is BA? Check whether they are commutative or not. Am I clear? Check whether they are commutative or not. Similarly, you have seen for lower triangular, no? You can do for upper triangular as well. Third one you write, let A and B are two upper triangular matrices. Then what is AB? Upper triangular matrix, if not, what is that? What is BA? Upper triangular matrix, if not, what? Whether AB is equals to BA or not. Clear? Understanding what I am speaking. Next, you take one upper triangular and one lower triangular. Multiply and see what you are getting. One upper triangular and one lower triangular, you multiply and see AB and BA. You can take order 3 for your. Don't take numbers. Take A1, B1, C1 like that. Don't take numbers A1, B1, C1 for any real. Am I clear? Anything I forgot here? This is what I want to ask. As far as I remember, one diagonal matrix you have and another matrix you are multiplying, it should be commutative. You are multiplying one triangular, two triangular, you should get triangular. Right? When you are multiplying one upper one lower, what I remember is we should get this diagonal. You check whether you are getting or not. In general, diagonal matrix na D1, D2, D3 is principal diagonal elements. In general, 3 by 3 matrix, upper triangular 3 by 3 matrix is A1, B1, C1, 0, maybe A1, A2, A3, 0, B2, B3, and then C3, all zeros. And then here, change the alphabets. Maybe you take all A's here, all B's there. Check whether you are getting or not. Tomorrow is holiday only, no, this much you can do. Everybody understood what I am asking. I definitely ask on Thursday. Right? I forgot about attendance. Sorry, I should mark attendance. Please don't leave my class. I want to mark attendance, my dear students. Please don't leave. I'm just calling the unmarked people alone. Ajay, Jose, Andrews, Arun Bharati, K.A., Mugan, yes, Harish M, Jagdish VR, J. Sarvanan, offline students also, if your name is there, please respond. Josiah Moses, Lohit, Padma Vinita, Chabarinathan, Shabarish Veeranan, Santoshini, yes, Gautaman, please be quiet. Dear offline students, yes, Gautaman is not there. Srinikesh, Sushant, where is your ID card? Huh? Left in home. Vasumati K, Yalini, anybody left ID card like Sushant? Your name is Afa. Ajit V. You two can go. Akhilesh S. You can also. You can go. Jeevataran. You can go. Not everybody. Mithun S. You can go. Thank you. Mohammed Saifuddin Amir. Your name. You are attending online. No, no. I have seen your name online. That's it. You can go. Muthuselvam. You can go. Muthuvel. You can go. Thank you. Naresh Balachandran. You can go. Santosh M. You can. Shiva Santosh. Yes. You can go. Sri Hariharan. You can go. Sushant. He went. Tanish. You can go. You are attending online. Or you changed batch? No, right? Offline only. Vishahan B. Okay, you can go. Yoga Srivatsan. Thank you. Remaining guys, what's your name? I marked absent. What you are doing? At that time?
I told you present only, sir.
Okay. Then done. Dear online students, you can leave. We'll see again in next class. I would like to say thank you for attending my class.
Thank you.